Alright, this is going to be the lecture video for chapter 11, where we talk about rotational dynamics and static equilibrium. So this is the outline of our chapter. We're going to talk about torque, angular acceleration, how it relates to torque, what happens when there's no torque, center of mass, dynamic applications of torque, angular momentum, conservation of angular momentum, rotational work and power, and of course, the vector nature of rotational motion. So, torque is the rotational equivalent of force. So, torque is a force that causes rotations to happen. So, for example, if you tighten a nut or a washer or something, when you rotate, you are making that force far away from the axis of rotation, aka where the nut or washer is. You want to be further away so that you'll have more torque and it's able to work properly. Or think of a door. When we open a door, we use the door handle, and the handle is on the complete other side of the axis of rotation. So the further away you are from the axis of rotation, the more torque that you're going to have to cause that rotating force. So torque is represented by this little fancy looking T Greek symbol. You can multiply the radius, or sometimes this is called the lever arm length. R is just how far from the axis of rotation is your force. And then you multiply it by the linear force being applied. So your units are newtons per meter. So if your force is increasing, then the torque is going to increase. They have a direct relationship. Also, if the distance away from the axis of rotation increases, then your torque is also going to increase as well. So only the tangential component of force can actually make a torque happen, aka your force either has to be at an angle or it's got to be tangent with your axis of rotation. Right? It can't be like this vertical component here. You're not going to get any torque that way. Only tangential and at an angle can you have a torque. So if you have angled force, then all you're going to do is take that distance and you're going to multiply it by the force, but times sine of theta. That's it. It's still in Newton meters. This is for angled forces. Regular torque is if your force is linear or in the same path. So if the torque causes a counterclockwise angular acceleration, we consider that to be the positive. Right? Counterclockwise in rotation means positive. Clockwise means that it's negative. So we can relate torque and angular acceleration together by using what we know from Newton's second law. We know that linear acceleration is force divided by mass. Well, now with rotation, you can take that same concept and apply it to angular acceleration. So if you know that your torque is the rotational equivalent of force, angular acceleration is the rotational equivalent of acceleration, and then your moment of inertia is your mass rotational counterpart, then you can say that angular acceleration is equal to the torque divided by the moment of inertia, or more commonly you will see written this way. So this is the linear counterpart of this Newton's second law with angular motion. So here's your comparisons again, right? I would add this table to your notes. This is super helpful. All right. When you have zero torque, or when all of your torques added together result in zero, we call that static equilibrium. This either happens when the object is at rest, right? Or if the net force of your objects is zero and your net force is zero. These two things are really important. If one of these two things doesn't happen, you're not in static equilibrium. The net force has to be zero in both directions, and the overall torque also has to be zero. So if your net torque is zero, it doesn't really matter what axis we consider rotation to be around. You just pick your frame of reference that makes the calculations the easiest. Right, so if you wanted to compare the two adults carrying the kid on the board, right, you could say where the woman's at, that can be your axis of rotation, or where the guy is. Whatever is going to make your math easier. And of course, it depends on what your problem is looking for. All right, so when your forces, of course, have both vertical and horizontal components, in order to be in equilibrium, we know that the components separately have to have a net force of zero. So net force of x has to be zero, and net force of y also has to be zero. So same thing from when we did regular forces linearly, it has to apply here as well. All right, center of mass. So if you have an object that wants to be balanced, you have to, of course, support it by its center of mass. Depending on the masses that are hanging, your center of mass is going to be different. It is going to be the place where your objects can balance nicely. So for example, in this picture, right, you have mass 1 and mass 2. Mass 2 is obviously bigger. So you're going to put your center of mass towards the smaller object so that it can compensate. So you can do trial and error to kind of figure out where your center of mass is by changing it from different axes and tracing a vertical line. And the center of mass is where the lines meet. So you can do this 2 times, you can do this 3 times, 4 times, as many times as you need to get a accurate center of mass measurement. All right, so when you have objects or systems that have both rotating and translating parts, remember translating just means linear, you have to make sure that you account for forces and torques correctly. All right, so free body diagrams are going to help you again, pictures, anything to help create a visual for you, just as long as you take into account the linear forces acting and the torques that are happening. All right, so just like everything else we've talked about, momentum also has an angular component. We represent angular momentum by capital L. And we know normal momentum is lowercase p is equal to mass times velocity. So the angular formula is moment of inertia I, so like mass with linear, times angular velocity. And the units are kilograms per meter squared per second. If you wanted to find, make the comparison between linear and angular momentum, you can do angular momentum equals radius again times mass times velocity, or radius times the linear momentum. Just like how we converted between angular velocity and linear velocity, angular acceleration and linear acceleration, like we did in the last chapter. You can do the same thing for momentum. So if your object, or in this case particle, is moving at an angle, then still the same formula, right? Except you're just going to add sine of theta on top of it, just like for torque. The units are still the same. Yeah, same equation. So when you want to find the rate at which angular momentum changes, right, you can rearrange your equation. So you would do your angular momentum divided by the change in time, right? So that's that rate. So you can break down it into moment of inertia times change in angular velocity divided by time. And this right here gives you angular acceleration. So you can also rewrite it as the sum of torques equals moment of inertia times angular acceleration, right? Newton's second law for rotation. But now you can replace that with change in momentum over change in time. It all relates to each other. All right, and just like with regular momentum, angular momentum is still conserved. If you have no net torque acting, your angular momentum is conserved. So, a couple of relationships to know. As your moment of inertia is decreasing, so that I is decreasing, your angular speed is going to increase, so the angular momentum doesn't change. So think about like a figure skater. If a figure skater is spinning and she has her arms out, stretching those arms gives you a higher moment of inertia, and she's not going to go as fast. But if she pulls her arms in towards her, that moment of inertia is getting smaller, and therefore she is getting faster. So you can also talk about work and power in rotation. So the work done at this time is just going to be done by the torque instead of the force. So work done is the torque times the change in angular displacement. All right, the work energy theorem applies here as well. The concepts are the same. You can also say the same thing for power. All right, power is the rate work is done. So for rotational motion, that means torque times change in angular displacement divided by time. Or you can say torque times angular velocity, which is the exact same as your formula for power when you relate velocity and force. Same thing. All they did was change the variables. Right, so we know that the direction of angular velocity is along the axis of rotation. You can use the right-hand rule to help you figure out the signs if you get confused. So for example, if you know the wheel is spinning and the velocity tangent goes this way, then you can curl your fingers to go in the same direction, and then whichever way your thumb points is the direction of your angular velocity and angular momentum, which also gives us the same direction of force. So remember, your thumb gives you the direction of the torque. If your tangential force goes in the direction of your fingers, whichever way they would curl. And only use your right hand. Don't use your left hand for these rules. It will not give you the same result. right? And then lastly, conservation of angular momentum means that the total amount of angular momentum around any axis must be constant. Right? It's conserved. It just doesn't go away. It has to stay the same as when it started, as when it ended. AKA, this is why gyroscopes are so stable. All right, in both axes, the angular momentum remains constant, causing it to keep spinning and not completely go off anywhere else.